So, in this process, so what is the basic principle in heat generation is resistance heating, Joule heating. So, we will see again physics of these processes. So, what is the main heat generation mechanism, how it is controlled, right, and what are the factors that can influence the welding characteristics, okay, and what are the factors that influence the heat generation. So, you say this Joule heating, but there are a lot of variants, factors that can influence heat generation in this process, right. We will see one by one. So, before that there are the number of types of resistance heating is used in industrial welding processes. Okay, it can be resistance spot welding, seam welding, projection welding, butt welding, flash weld welding, resistance offset welding, okay, or electrical resistance welding, and there are so many types, but the fundamental heat generation mechanism is the same, which is Joule heating. Okay, so what is Joule heating? The heat generated when you pass ampere of I, voltage of V over a unit time of t, right. The heat is generated is given by I square R or I times V times t. So, it is difficult to get V all the times, it is easy to measure the resistance. So, we always replace with resistance, right. So, what is the relationship? V equal to IR, okay, and then so we replace V with an IR, then it becomes IR square. So, you always remember, so ampere and then volt and second becomes Joule, isn't it? So, that is from the basic definition of the ampere and volt. So, you need to understand that to generate heat. So, that is how we also use water heater, right. So, that is also use the same principle. So, here in the Q is the energy per unit time, the time is given. If you move joules per second and second to this side, it becomes Joule, right. Joules per second is watt, it is watt, right. So, then the heat generated in joules, it is nothing but the current square times resistance. And what is this R? What resistance we are talking about here? Electrode resistance. So, imagine now I want to weld two sheets, okay, something like this. Okay. Somewhere say suppose I want to weld at the middle. So, what is R for this configuration? Sheet resistance, bulk resistance, that is it. So, R of this and R of that will determine the heat generation, yes or no? Say suppose you have an electrode, you use an high conductivity copper, okay. Similarly, you have another electrode on the bottom, is it? And what are the resistance you expect in the circuit? Electrode resistance, sheet resistance, that is it. Contact resistance, okay, good answer. So, where is the contact resistance here? Between the electrode and plate, between the plates, exactly, okay. In this case, the main resistance that dictates heat generation is the contact resistance between the plates, okay. So, before that the contact resistance can be generated in various configuration, okay. So, for example, resistance spot welding. So, these are the variants of resistance welding, various types of welds you can expect. There are 6 major types of process used in a direct resistance heating. Resistance spot welding, so we use a simple 2 electrodes to make a spot on the weld spot. Again we will see in the subsequent classes. And the resistance seam welding. So, what is seam welding? To make tubes. in most of the applications in tube making is done by resistance seam welding or ERW, it is called electrical resistance welding. So, where the sheets are folded and then we pass a current in between the interface, heated by the contact resistance, and then I do an upset to push it once it is heated up, and then we deform the edge to make a continuous seam. Or we can also, instead of having a spot electrode, so you have 2 plates and you have an electrode rolled along the interface continuously, you form a continuous seam of welding. Okay. Then radial electrical, that is resistance seam welding with low frequency or high frequency, or you can also use an induction heating, use a resistance of the contact as well as the external heating mechanism, and you can also increase the heating efficiency. Or you can also do projection welding, okay, or flash butt welding, where you form an arc between the 2 faying interfaces, you melt and then subsequently do an upset, so the molten liquid can go away, and then you can have a joint. Or you can also do simple upset welding by resistance heating. For example, you do not melt, just heat it up to higher temperature and then upset it so that it forms a joint. Okay. Or you can also do percussion welding. So, we look at all these processes in this unit. Okay. So, what are the important factors that control the heat generation, and what types of electrodes we use, why should we use this process for what application. Okay, we all see this in this unit. So, that is what we are going to see in this lesson. So, how the fundamental that governs the welding processes to make such welds, because then we can improve the weld metal property. Okay, so, first process what we look at is resistance spot welding. As I said, it is very widely used in automotive industry, resistance spot welds. Okay, so all the thin sections, they are all welded with resistance spot welds. And basically what we do in resistance spot welding is a simple setup, is very extremely simple. So, we have 2 electrodes, okay, top electrode and the bottom electrode, and generally these electrodes are made with copper or copper alloys. Okay. So, we use copper because high conductivity, right, and we can also extract heat from the electrode very effectively, because during this process the electrodes would not melt, is not it. So, when you pass the current, you keep in the top electrode and bottom electrode, and then we attach the sheets to be welded in overlap configuration. What is overlap? Lap. Okay. So, top of each other, something like this, and then we fix the electrode on the top and bottom, and then we pass a current. And during this process, we will have to make sure that only the interface melts. We should not be melting the electrode, is not it? Then we have a problem. We should not heat up the electrode, because we are also applying a force, an axial force during this process. So, in this case, you make sure that temperature is not increased. So, what do we do? So, we use a copper electrode and we cool the electrode very effectively by circulating water, right, it is clear. So, the copper electrode generally we use, and then the heat can be transferred very effectively, because thermal conductivity of copper is also very high, right. So, we can pass a current, and the current can be flowing through the faying interface. What is faying? It is a very nice British word, English word, not British word. To fay means to join. Okay. Okay, so the faying interface over here, and then we will have to make sure that the current flows, and during this process, if current continuously flows, then you do not have an effective heat generator, is not it. So, we need to have some resistance R, right. So, what happens when the current actually flows? So, whenever there is a hindrance to the current flow, that is resistance, is not it. So, that is where the charge accumulates, and then the charges can interact, can collide and dissipate heat, is not it. So, any movement is hindered, that means that the energy is dissipated. So, now in this case, if a current flows from one electrode to electrode, make it positive or negative, whatever way, right, and generally we use an AC current in resistance spot welding or resistance welding. for a very specific region. So, we will come back to that later. So, imagine now you pass an alternating current. In every cycle positive negative is changing, and sometimes electrons can flow in this direction, other times electrons can flow in this direction. But ultimately the flow of electrons are hindered by the various resistance in the system. So, what are resistance in the system you can explain, you can expect, say when the current is flowing from this direction to this direction, from top to bottom. What are the resistance you can explain, you can expect? Okay, first resistance is the resistance of the electrode itself. So, in this case say R1, okay, R1, right. So, generally we use high conductivity copper. If you use, then R1 is very minimal. Okay. The second resistance you would expect is the resistance between the electrode and the top of the sheet. Similarly, the resistance between the bottom electrode and the bottom sheet. That means the resistance R2, say R1 is, say for example copper, and then R2 is between copper plus workpiece surface, right. So, this is R2, and then what are the resistance you expect? Okay, so before that you also have the bulk resistance of the workpiece itself, okay, R3, and then you may have the resistance between the workpiece, that is R4, which is the contact resistance. Which resistance will be maximum? Obviously, the contact resistance between the two sheets, okay, right. So, because R1 is as small as possible, similarly the R3 resistance of the sheet is not as high as in the R2, okay. So, the maximum resistance you would expect is in between the sheets. So, that is where you expect the electron's path is hindered maximum, is not it. So, that is why the R4, the contact resistance can generate a maximum heat, okay. So, that we can make it for our own benefit, because we will have to melt the interface, okay. If a charge carriers are hindered at the interfaces, then the heat can be accumulated at the interface, and that can lead to heat generation, ultimately melting of the interface, okay. So, in these 4 resistances, the main rate controlling resistance, which is actually form the well nugget, is the R4, the contact resistance, okay. The contact resistance is not a bulk resistance, okay. So, bulk resistance is a material property, okay. Contact resistance is depending on the surface roughness, okay, and the surface condition, okay, and then how hard you press each other, is not it, the load you give actually, these all influence the contact resistance, okay. The surface conditions, for example, you may do on a bare sheet, and another case you use on a coated sheet, so then the contact resistance is entirely different. Similarly, you use now say the 2 kilonewton load, in other case 5 kilonewton load, which will have maximum contact resistance? So, obviously 2 kilonewton, because when you increase the load, you also decrease the, or you also plastically deform, you reduce the surface roughness. So, you are bringing close to each other, is not it, right. So, you change the load, you also change the contact resistance. So, the contact resistance, in other words, the heat generation is a function of various parameters, which involves the material surface roughness, material surface conditions, the load you apply, okay, and then that will determine the heat generation. So, if you look at the temperature distribution, I put in this case in the other axis, the maximum heating would happen at the interface, is not it. So, this is welding temperature as function of distance. So, you would expect some or other heating at the top of the surface, okay, because the R2 is also in a contact, it is not a bulk resistance, but luckily the heat whatever you form at the R2 is extracted, is not it, by the water cooling. So, the temperature will not reach as high as in the interface, okay. And similarly, the R1 is minimal, the copper resistance of the copper if you use the copper electrode. So, you won't expect any contribution from the R1 to this process, and same goes with R3. R3 also is very minimal because that is the bulk resistance of the sheet you are welding. So, if you look at this entire the setup, resistance spot welding, the main rate controlling resistance is the R4. Yes, the R4 leads to the heat generation, heat accumulation of the interface, and then because of that you start melting first the interface and then it will grow and you form a weld covering both the sheets, and that is what is known as nugget, weld nugget, right. We will see. So, it is clear, right. So, how we control the heat generation. So, heat generation during resistance spot welding is actually controlled by the R4. The R4 is the contact resistance between two welding interfaces. Yes, it is clear? Good. So, this is what happens if you look at I put on a schematic again. So, you have a top electrode and bottom electrode, and you keep two electrodes. So, basically, so you need to apply a compression load, and the sheets are placed in an overlap configuration. You pass a current and simultaneously you also apply a load, and then you start melting at the interface, and then the interface would grow and make a continuous weld joint. So, now the size of the weld is determined by the thickness, right, and the contact resistance, as well as the load you apply and the welding time, is not it, right. So, thickness is a mass effect, okay. So, Q would be function of the mass effect, and then the current, basically the R is a contact resistance. So, R can be R1 plus R2 plus R3 plus R4. So, you can neglect R1 and R3, and R2 also you can neglect significantly because you are extracting the heat. So, the R4. The R4 is again a function of the load, as well as for given surface conditions the R4 can only be changed by sigma, by the load, right. How much you load apply, is not it, because material is selected already, right. So, that you can't change for a given material. The actual weld nugget size is determined by the current you give, and then the R, which is in turn determined by R4, R4 in turn determined by the load, right. It is clear. And then you have T. What is T? The time of welding, how much time you spend. So, based on these three factors we can calculate the weld nugget size, okay. So, the size of the weld, right. So, because these factors, the current, the R4, R4 and then in turn sigma, and then welding time will determine the amount of liquid you form at the interface, okay. So, if you look at the temperature distribution again, if you look at it, so you will have maximum heating. So, resistance you expect at the interface, therefore, the maximum temperature at the interface, right. It is clear. You have minimum heating because you have a minimum resistance for the flow of current, is not it, and you also have a small variation in the temperature, and this is due to your R2, oh sorry, it is, what do you do that interface, what I give R2, and this is R4. That's clear, right. So, the main rate controlling is R4. R4 can be changed by surface condition. If surface is fixed, material is given, R4 can be changed by the load, and then other factors will influence the welding is the current and the welding time, right. It's clear. Good. So, if you look at a cross section of a typical resistance spot weld, this is how it look like. So, the electrode, so we made a cross section and parallel to the axial direction of the electrode, and you have electrode, you have a cavity inside to have a water circulation, isn't it? Right, and then you place sheets to be welded in overlap configuration, and you apply a load and the current, and during this process the heat is generated at the interface, and interface would start melting and then forming a weld nugget, very beautiful weld nugget at the center of the electrode and surrounding area. It's clear? Good. So, this is a typical weld thermal cycle we follow. What is weld thermal cycle? I said, okay, it's because we always need heat, right? We pass a current and simultaneously we also apply some load. And in a conventional resistance spot weld thermal cycle, so you have a current versus force. Generally, we have such a curves. So, this is done to 1.2 mm sheet in overlap configuration. Right. So, what you do is, so once you have an overlap and you start first applying a load, upon applying a load which is required to achieve a required the contact resistance, then you will start passing the current. Okay. So, for 1.2 mm sheet, in this case I used 5.5 kiloamperes, isn't it? In a conventional GMAW, what is the current we use generally? Okay, not more than 300, 400 amperes, whereas here we can go as high as 10 kiloamperes. So, in the equipment what we have in our lab can go up to 10 kiloamperes. Okay. So, in order to get a good weld diameter, okay, good weld diameter is determined by some factors, we will see in subsequent lectures. Okay. Suppose if you want to achieve an acceptable weld diameter, so in this case we can go up to 5.5 kiloamperes with a load of 3.5 kilonewtons. Okay. So, we apply a 3.5 kilonewton load, and during this process we also apply a current of 5.5 kiloamperes, and then you decrease the current, you keep the load intact for some time so that metal solidifies. Okay. Otherwise, if you take it up and the liquid can separate out. So, you keep the load for some time more, and then ultimately you form a weld nugget. And if you look at the entire weld cycle, in this case 340 milliseconds, okay, close to 350 milliseconds, right. So, that is a very fast process, isn't it? So, in this case, in a resistance spot welding, in most of the cases we use AC, alternating current.
Which one is current, which one is?
In this case, blue is current, pink is that is what I said, 5.5 kiloamperes. Okay. So, this is amperage and this is load. Okay. So, most of the cases we use alternating current for a very specific reasons. Again, physics, why we use alternating current here, and if we use DC there is a problem. Okay. So, we can now assume that we use only AC, and we will see why only AC in later classes. So, generally the current is from kiloampere to we can go up to 10,000 kiloampere, even much beyond that, okay, based on the equipment capability and our need. As I said, the contact resistance determines heat generation. So, R, because the contact resistance inversely proportional to the load. Load increases or decreases, isn't it? Why? Because we are bringing plates close to each other. If you are pressing more, we are bringing the plates close to each other, and because of a very tiny area what you look at, and we also have an electrode which is effectively transferring the heat from the weld, and this electrode itself is water cooled. The cooling rates what we achieve when the weld solidifies, it can be several thousand Kelvin per second. Okay. The cooling rates can be as high as 10,000, 2000 Kelvin per second. Okay. So, entire weld you can touch in 300 milliseconds, right. So, if you are cooling such a high cooling rates in a steel, obviously in most cases you will get only martensite microstructure. So, weld can be very brittle, but we will have to live with that. We will have to play around with our welding parameters such a way that we achieve a good weld metal property. Okay, we will also touch upon some of the aspects when you study that. So, you can now assume that the main characteristic of this process in this case, the heat is generated by the contact resistance, which determines heat generation, the R4. Okay. And then we also apply a load, and the load can change the contact resistance. And then the welding time and the current would determine the weld size. We use mostly alternating current. The reason is, so it is known as a Peltier effect. For next class you can come up with the answer. So, what is Peltier effect? Okay. So, next class we will discuss why we use only AC, okay, because of this effect. And then because of the effective heating, cooling done by the electrode, the cooling rates can be extremely high, in thousands of Kelvin per second. Yes, it's clear? Good. So, we will stop with this and then we will see in next class.